There is a direction in space so difficult to reach that getting there requires 10 times more energy than flying to Pluto. Scientists have spent decades trying. A spacecraft launched in 1990 had to slingshot around Jupiter just to get a partial look. And what it found up there above and below our own sun rewired everything we thought we knew about the star keeping us alive. The sun's magnetic poles are on fire in a pattern no model ever predicted. We are sitting inside a bubble whose true shape we still cannot see. And the biggest comet ever discovered is already on its way inbound. Here's something that will mess with your head. Right now, you are moving at 67,000 miles per hour. Not toward anything. Sideways, around the sun. Every second, the ground under your feet slides 19 miles in a giant circle, and you feel absolutely nothing. Every rocket we have ever launched inherits that motion. Every probe, every satellite, every spacecraft, all of them are already screaming sideways before the engines even ignite. For most missions, that is a gift. Going to Mars, you barely need to adjust. You are already heading in roughly the right direction. But the moment you want to go up straight up, out of the flat disk the planets all share, that sideways speed becomes a wall. To go straight up, you first have to cancel all 67,000 miles per hour of inherited motion. Every last bit of it. Then, and only then, can you start climbing. The total energy required is nearly 10 times what it takes to reach Pluto, a frozen rock 3.5 billion miles away. Think about that. The far edge of our solar system is easier to reach than a point just a few million miles directly above our own star. That is not a distance problem. That is a speed problem. And it has kept us pinned to a single flat sheet of space for the entire history of human spaceflight. We can go sideways forever. We can hop between planets like stepping stones. But step off the disk? Physics will not let you do it cheaply. And because of that, the space directly above and below the sun has been, until very recently, the last true blank spot on our map. What lives up there has been a mystery for a long time. It is starting to stop being one. And what we are finding is not what anyone expected. Look straight up from the sun's equator and you are staring at its poles, the north and south tips of our own star. For most of human history, we have watched the sun from the side. Every telescope, every satellite, every observation ever made all of it from roughly the same angle. Like trying to understand the weather of an entire continent while you are only ever allowed to stand at the equator. You can measure a lot, but you are missing the most important part. The poles of the sun are where the real action happens. The fastest solar wind in the entire solar system pours out from there, particles screaming outward at 750 miles per second, nearly double the speed of the slower wind near the equator. The sun's magnetic field completely flips itself north, becomes south. South becomes north every 11 years, and that violent reversal begins at the poles. The space weather that affects your GPS, your power grid, your satellite TV, all of it, is shaped by what happens up there. And for 35 years, we could measure it but never photograph it. A spacecraft called Ulysses launched in 1990. To get any kind of polar view at all, it had to fly all the way out to Jupiter first, use the giant planet's gravity like a slingshot, and bend its path nearly 80 degrees out of the plane. It worked. Ulysses flew over both poles 3 times across 18 years of operation. It felt the fast polar wind. It measured the magnetic environment in detail no one had before. It carried no camera capable of taking a single photograph. We had been to the poles of our own sun and come back with numbers but no pictures. Like visiting the Grand Canyon blindfolded. That finally changed in March of 2025. The European Space Agency's solar orbiter had spent years quietly bending its orbit, using gravity assists from Venus to tilt its path further and further out of the plane. In March, it tilted far enough, about 17 degrees below the sun's equator, to look down at the South Pole and send the images home. They were the first photographs of a solar pole in the entire history of our species. And the roof of our house was on fire. Scientists expected something like what we see from the side, banded, structured, relatively ordered. What Solar Orbiter sent back looked nothing like that. The south pole of the sun showed a chaotic, tangled knot of magnetic fields. North and south polarities jumbled together in the same region at once. It was the fingerprint of a star near the peak of its cycle, gathering itself to flip. The full pole-to-pole data finished arriving later in 2025. For decades, researchers had been describing the roof of our own house from the ground, guessing at it from models and indirect measurements. When they finally saw it directly, the roof was on fire in a pattern no model had drawn. Now here is where something else enters the picture entirely. While scientists were processing those first polar images, a separate discovery was quietly sitting in the data, one that had been confirmed years earlier, but is only now getting the attention it deserves. In 2021, astronomers announced the discovery of Comet C 2014 UN271, nicknamed Bernardinelli-Bernstein after the researchers who found it. And the numbers attached to this thing are staggering. It measures roughly 85 miles in diameter. That makes it 12 times larger than Halley's Comet, and nearly half again as large as the previous record holder. It is, by a significant margin, the biggest comet ever discovered, and it is heading inward through our solar system right now. Its closest approach to the Sun is expected around 2031. At that point, it will come no closer than roughly the orbit of Saturn, so there is no collision threat to Earth. But a comet of this size passing through the inner solar system is an event with no modern precedent. Astronomers are watching it closely. The Hubble Space Telescope has already captured images of its nucleus. The solar poles are mid-flip. The biggest comet in recorded history is inbound, and we are only just beginning to understand the bubble we are all living inside. There's one more thing up there that scientists cannot stop thinking about. Around the Sun, in every direction, there is an enormous invisible bubble called the heliosphere. It is the region where the solar wind dominates, pushing back against the thin gas between the stars. Everything you have ever known sits inside it. Every planet, every moon, every probe we have ever launched. The heliosphere is our shield. It deflects a significant portion of the cosmic radiation coming from the rest of the galaxy. For decades, textbooks drew it shaped like a comet, a rounded front facing the direction we travel through the galaxy, and a long tail trailing behind. In 2020, a team led by Mehrav Ofer at Boston University, using a new model based on NASA data, came to a completely different conclusion. The heliosphere is probably not comet-shaped at all. Their leading version looks more like a deflated croissant, a curved central bulge with two jets curling off the sides and no tail. Other teams still argue for the tail. The real shape is genuinely unsettled. And the reason we cannot resolve it is simple. We have never seen it from outside. Every measurement we have is built from models and from particles counted from within. The two Voyager probes crossed the edge of the bubble in 2012 and 2018, but they crossed it sideways, nearly flat along the plane of the planets. They told us about the wall at 2 points. They could not show us the whole shape from above. To see our own home's true form, a probe has to do the one thing physics keeps making nearly impossible. Here is the counterintuitive part. You cannot solve this by building a bigger rocket. The fuel required to cancel 67,000 miles per hour of sideways motion by brute force is beyond anything we can realistically launch. So the way up runs in the opposite direction from every instinct. Instead of pointing your engines at the sky and climbing, you drop the spacecraft toward the Sun. You let it fall inward, accelerating under solar gravity, until at its closest approach it is moving at over 60 miles per second. Then, at exactly that moment, you fire the engines. A rocket burn is dramatically more efficient when performed at high speed inside a deep gravitational well, a principle first written down by physicist Hermann Oberth in 1929. The same fuel gives you far more energy at that point than it would anywhere else in the solar system. The dive becomes the launch pad. This is not a thought experiment. It sits at the heart of real mission proposals being studied right now, including concepts targeting launch windows in the early 2030s. If one of them makes it, a camera will finally look down on our solar system from above. It will see the disk the planets ride. It will see the true shape of the bubble we are breathing inside. It will photograph the poles of our star from directly overhead. The closest photograph there is and the only one we have never been able to take. We have driven rovers across Mars. We have dropped a probe through the clouds of Saturn. We photographed Pluto from less than 8,000 miles away. But the space directly above and below our own sun, the poles of the star that makes all of this possible, we have only just begun to see. And what we are finding up there is stranger, more violent, and more important than most people realize. The poles are mid-flip. The shape of our shield is unknown. The largest comet ever recorded is making its inbound run. The answers are coming. The question is whether we will have the instruments in place to understand them when they arrive. If you made it this far, you already know this stuff matters. Hit that subscribe button and ring the bell. Every week we cover the stories about space that most channels are not touching. And drop a comment below. We have got a lot more coming. And the next one picks up right where this left off. Stay curious. We will see you there.